This is the continuation video in the playlist of geometrical isomerism. In this video, I'm going to discuss geometrical isomerism in CN double bond and NN double bond system. It is very clear all the compounds related to CN double bond and NN double bond we are going to discuss, and very clear here CN double bond and NN double bond, these are the geometrical centers. The rigidity of the molecule is again due to the presence of a double bond. In this, the first category we are dealing, that is oximes. Geometrical isomerism in oximes. First, let us take what is meant by oxime. What are the two types of oximes? What is the condition to show geometrical isomerism in case of oxime? Finally, what type of configurations we use in case of oximes? So in that first point we have to talk about, that is what is the exact meaning of oxime. Oxime is an organic compound having C double bond N system, and N is attached to OH group, hydroxy group. And of course, there will be one lone pair on nitrogen. This is the oxime structure. For the sake of convenience, I'll be calling this particular carbon as oxime carbon. For the sake of convenience, the carbon present in that C double bond N, that carbon I will be calling it as oxime carbon. And these oximes are basically classified into two types. They are aldoximes and ketoximes. Aldoxime is obtained from aldehyde, ketoxime is obtained from ketone. Basically, oximes are obtained when aldehydes and ketones react with the hydroxyl amine. Condensation will take place. Due to the removal of water, oxime will be produced, but at this point of time, need not to learn these reactions and all. You have to identify whether geometrical isomerism is possible or not. What is the name of that functional group? In case of oximes, if oxime carbon contains at least one hydrogen, then it is called aldoxime. If oxime carbon does not have any hydrogen, if both are alkyl groups, in that situation, that is called ketoxime. So oximes are classified into two types. The first one is aldoxime, second one is ketoxime. And this is about oxime classification. And the condition to show geometrical isomerism is very clear. The same condition, whenever you are talking about oxime, by default, nitrogen is having two different things. One is OH group, another one is lone pair. So as long as you are saying oxime, these two are fixed in case of nitrogen. So the one condition with respect to nitrogen, the condition is satisfied. Only you have to observe oxime carbon. The two groups attached to oxime carbon must be different. Here if you have A, this must be B. That means these two must be different groups. In that situation, geometrical isomerism is possible. Rigidity of the molecule is due to the presence of carbon-nitrogen double bond. Two types of configurations. One is syn-anti configuration. Of course, another one is EZ configuration. EZ configuration, that is purely based on CIP rules. Apart from that, we can also give a syn and anti configuration. What is syn, what is anti, how to give the configuration, we will discuss in 2-3 examples. But before going to syn anti configuration, another important point here, Formaldoxime and symmetrical ketoximes do not show geometrical isomerism. So if you want to write the structure of a formaldoxime, that is oxime obtained from formaldehyde. In case of formaldehyde, so that carbon both are hydrogens, and this is a formaldoxime. Formaldoxime, here the group and here also the group both are same, therefore geometrical isomerism is not possible. In case of symmetrical ketoximes, that is, this is ketoxime structure we are writing. Symmetrical ketoxime, which means both are same alkyl groups. These two groups are same. Both can be methyl groups, otherwise both can be ethyl groups, whatever it may be. Whenever these two groups are same, geometrical isomerism is not possible. So formaldoxime and symmetrical ketoximes do not show geometrical isomerism, and we have two types of configurations to represent geometrical isomers of oximes. One is syn anti configuration, another one is EZ configuration. In case of syn anti configuration, if you are dealing with the aldoximes, the simple logic, if a hydrogen of oxime carbon, OH group of nitrogen, if these two are same side to the double bond, then it is said to be syn form of oxime. If a hydrogen and OH are opposite side, then it is said to be anti-form. That is the fundamental rule you have to follow. Here, in case of oximes, it is fine. Hydrogen and OH we are taking reference. Hydrogen and OH orientation we are taking, we are considering. But in case of ketoximes, hydrogen is not available. In that case, for each geometrical isomer, we can give both the names. Every geometrical isomer we can give syn name and anti name. So what is the rule we have to follow? In order to give this particular configuration in case of ketoximes, again you take OH as reference. You just check for OH which group is same side, which group of oxime carbon is same side, which group of oxime carbon is opposite side you take. If you want to give syn name, OH group, and which group is same side you check. And the name of this group is para-toluene and name of this group is phenyl. In this orientation, para-toluene and OH group, these two are same side. Therefore, if you are starting the name with syn, which group is the same side? Para-toluene is the same side. Therefore, para-toluene, after that another group, that is phenyl, and finally you have to add ketoxime. For the same structure, for the same spatial orientation, you can give anti-name also. If you want to give anti-name, you have to see which group is opposite to OH. Here OH and phenyl group, these two are opposite side. Therefore, you start the name with anti and mention the group which is opposite to OH group. After that, this group you have to name. Therefore, anti-phenyl para-toluene ketoxime, like this. In this case, second example, if you see, it's a geometrical isomer. In order to give syn name, now this is OH group, phenyl group is the same side. Hence, we are saying syn phenyl para-toluene ketoxime. In case if you want to give anti name, you have to mention the name of this particular group first. Therefore, anti para-toluene phenyl ketoxime. So this is about syn and anti nomenclature. If you want to give EZ configuration, already the rules, CIP rules, you have to follow the CIP rules, no doubt. So first you have to give the priority. OH and lone pair, OH gets the first priority, lone pair gets the second priority. Similarly, methyl group gets the first priority, hydrogen gets the second priority. High priority groups are opposite side. Therefore, this is said to possess E configuration. In case of antiform, you can see only spatial orientation is different. OH gets first priority, lone pair gets second priority. Here, methyl receives first priority, hydrogen is getting second priority. High priority groups are same side, therefore this configuration is Z. Similarly, in case of ketoximes, you can follow the same thing. So OH first priority, lone pair second priority. Here you have just hydrogen, but here you have methyl group. So up to here the structure is the same. The deciding factor is here we have hydrogen, here you have methyl group. So this will receive first priority, this will receive second priority. You can see high priority groups are same side, therefore it is Z, and exactly if you decide you will get E configuration here. This is about oximes. Now let us move on to the second category, azocompounds. First you have to know what is azocompound. In case of azocompound, there is N double bond and a nitrogen is attached to one group. It can be alkyl group, phenyl group, whatever it may be. Here I am taking phenyl group. So this particular structure is called azocompound. Azocompound. In case of azocompound, we use syn anti-nomenclature, and if you want you can give EZ configuration also. EZ configuration also we can give. Only thing you have to follow CIP rules. In case of syn and anti, it is very clear. If lone pairs are same side, then it is a syn form. If lone pairs are opposite side, then it is anti form. So this is about geometrical isomerism in azocompounds. And other cases, if you take imine, not amine, this is imine. In case of imine, the same condition, there is carbon nitrogen double bond. Here there is an alkyl group, another part is lone pair. So two different groups are present always. It can be hydrogen also, no issue. And here if the two groups are different, then geometrical isomerism is possible. Here if the two groups are same, in that situation geometrical isomerism is not possible. Same thing, need not to remember the names at this point of time. However, all these structures you will get to know in one chapter called carbonyl compounds, and this is a hydrazone. In case of hydrazone, there is carbon nitrogen double bond, and this is attached to NH2 group. This is lone pair. And here if carbon has two different groups like A and B, then geometrical isomerism is possible. You can use EZ nomenclature. EZ nomenclature we can use. And the next one, phenyl hydrazone. In case of phenyl hydrazone, this is a C double bond N. This nitrogen is having C double bond N. Nitrogen is having NH, PH, another one is lone pair. If the groups attached to carbon are different, then geometrical isomerism is possible. The configuration we use is a EZ configuration. And one more example, 2,4 dinitrophenyl hydrazone. Already I told you, need not to remember the names at this point of time. But since names are available, I'm just giving. And if these two groups are different, then geometrical isomerism is possible. So this is about geometrical isomerism in carbon nitrogen double bonded system, nitrogen nitrogen double bonded system. Let us just take one question randomly. So this will receive first priority, lone pair receives second priority. In case of methyl group and ethyl group, you can see all are hydrogens, therefore it is 1 1 1, but two are hydrogens, one is methyl group, and it will be 6 1 1. So this will receive first priority, methyl gets second priority. You can see high priority groups are opposite side, therefore this molecule is said to possess E configuration. So this is about geometrical isomerism in C-N double bonded system, N-N double bonded system. Thank you very much.